The last thing I want to cover today will be some of the kernel extensions that Android does to go above and beyond what you'll find with Linux in order to customize Linux and the Linux kernel for the needs of mobile devices. And we'll see that the big theme that pervades all this stuff is trying to make the Android stack run more efficiently and effectively on memory and power-limited hardware. And we'll also talk a little bit about how they speed up performance for inter-process communication between the processes on the same device. So let's first talk about memory management. So we talked before about how Android Linux leverages the device memory management capabilities that Linux gives you, but it tries to go above and beyond them to make it optimized more for mobile devices. So the GNU Linux kernel, the one that started out with, shields programmers from constraints of primary storage, where you don't have sort of as much RAM as you do flash, by using essentially paging. So you can basically pull things in from flash into memory and thereby give people the illusion that they can write applications that are actually bigger than the amount of RAM. Now, it's kind of unlikely you do this a whole lot, because that would be a rather big application to run on a phone. On GNU Linux, they have this concept called swapping, which says when main memory starts to fill up, the operating system will take portions of the contents of apps running in main memory and move them back to secondary storage to free up primary memory. That's called swapping. Now, it turns out that Android Linux behaves differently than classic GNU Linux because of the constraints of mobile devices. So one of the things it does is to conserve power, it doesn't actually provide swap space. And the reason for that is that copying the contents of RAM-oriented memory, main memory, back to flash memory would consume a fair amount of power. And they're trying to not tax the battery, which is a good thing, because batteries tend to run out. And batteries typically don't improve at the same rate that, say, processor speeds or memory do. So it pays to optimize for power. So what that means is if things are changed in main memory, it's not automatically written out to swap space. Instead, what they do is they're starting to run low on memory, rather than writing the app back instead of having the app transparently written back to secondary memory, they define something in Android Linux called the low memory killer. And the low memory killer is a device driver that runs in the Android Linux kernel. And when you start running low on memory, the low memory killer will go around and terminate app components in a sort of willy-nilly way. I think they try to be smart about it, but the point is that they'll look for app components to terminate, as in the Terminator, and they come along and basically shut them down. And you get a very particular and idiosyncratic set of callback hook methods that will be dispatched to your app code right before a process is terminated. And you get a very short window of time to save state that's important to you before your process gets killed. And as a result, you have to know about various things to save that state, right? You have to know how to save the state, and there's a variety of different ways to be able to do that. And the way to do this is to properly implement these lifecycle methods on Android components like activities and services. So we won't have enough time to really do this justice, but in a nutshell, the application components like activities, which are the user-facing components, and the background stuff like the services, these are potentially going to be terminated rather abruptly by the low memory killer if you start running low on memory. And so what you need to do is know how to implement various hook methods like on pause and on stop and so on, because those are the chances you get to save your state before your process gets killed. And typically what you do is you write code that will deallocate resources at the right point of time. And usually it's in the on pause and or on stop methods. On destroy is kind of a wacky case because it doesn't always get called before something gets terminated. There's also a whole pile of patterns or idioms that are documented in the Android website that tell you how to manage your application memory. You can see some of the things here, like, here's some tips. Use services sparingly. Release memory when your user interface becomes hidden. Release memory as memory becomes tight. Blah, 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 blah. Lots of things like that you should try to do to avoid using too much memory. The good news is, as we get more and more memory in these mobile devices, this becomes less important, but it's still something you have to think a lot more about in a mobile device than you would on a laptop or a server. And again, there's tips and tricks you can apply to do things like reduce the size of your apps to try to reduce the amount of memory consumption. And there are also some tools that you can use to analyze your app's use of random access memory. And if you read the documentation, it tells you where to find these things. Android Studio also has some tools to help you with this as well. There are some situations where you might want to share memory between different applications. Once again, the theme being to try to reduce the amount of memory that's being used by not duplicating the storage across all the apps, but instead having them share the storage in some way. And there's a couple different reasons to do this. One is just to only have the content stored once, but still make it accessible very rapidly. And the other thing you might want to do is use this as a way to communicate from one app process to another app process without having to copy the data multiple times through the operating system kernel. So this is something called Android Shared Memory, or Ashmem, which is another non-standard feature that's provided by the Android Linux kernel. Internally, the Android Binder framework uses Ashmem to optimize the transfer of blobs, binary large objects, by avoiding data copying. So they simply map the information and then share it through shared memory. The Android shared memory is optimized, once again, for devices with limited RAM. You will not find this abstraction available in regular GNU Linux. It's only available on Android Linux because they're not trying to solve the same set of problems on GNU Linux. And some of the things that they do is, if you start running low on memory, then Ashmem will start discarding the shared memory regions in order to be able to conserve space. So once again, this is really as an optimization. You have to be careful you don't put things into shared memory that you really care about without having it stored persistently through some other means. Likewise, when your apps exit, then the shared memory segments are automatically released. Once again, to release the memory back into the memory pool so it can be used by other apps, thereby conserving the memory. Power is also a big deal. So because of that, hopefully I don't have to motivate why power is a big deal for a mobile phone. It drives me crazy. For some reason, even though I'm running one of the later versions of Android on my mobile phone, over the course of a day, certain services run in the background, or certain apps are taking up memory and running in the background, so my battery utilization tends to go down the tubes unless I go in and manually optimize it. There's an optimize setting that you can enable, which will shut down those background apps. It's kind of annoying, but it does make it run longer between charges. And they provide these features in the operating system kernel. Some examples of things that will burn battery very quickly is keeping the screen on for too long. If you have a mobile phone, you probably know you can change how long the screen stays on. And if you set it for, between uses, if you set it for like 15 or 30 seconds, then it's a little annoying because it'll go dark a lot, but you save a lot of battery power. If you keep it on all the time, you'll burn through the battery in no time flat. Likewise, keeping the CPU running when it's not being used is another way to burn out the battery. They have a bunch of features built into the Android Linux kernel that control when devices sleep and wake, and they're called sleep locks and wake locks. And there are various ways to control these kinds of things. You can also basically come and inspect in your phone and see, what's taking the longest, what's using the most amount of battery, and that's what those optimizer tools do. They go and shut those things down, or dim the screen, or reduce the brightness, or whatever it needs in order to be able to make it work better. And they have these things called wake locks, and there's certain apps that need to keep running even if you haven't touched the screen in a while. And the most obvious things are stuff like navigation apps, right? You're trying to drive somewhere. Well, you'd be really annoyed if every 30 seconds the screen went blank, right? And similar things would be YouTube, where you're watching a video, and if you're probably not sitting there compulsively touching the screen while you're watching the video, but they have to keep those things they have to keep the phone from going idle even though you aren't touching it or interacting with it. So there are these things called wake locks that are used to manage that, and they're handled in the operating system kernel in various ways. Not the typical kind of thing you'd program as a sort of a naive application developer, but if you're writing things like your YouTube or your maps and so on, then you probably would want to use this stuff. I also mentioned that Android has some cool optimizations for inter-process communication, and that's because TCP/IP was originally designed for remote communication, in other words, across a LAN or a WAN. So it's got all these extra protocol features in there for things like slow start and exponential backoff. If you take the networking class, I'll explain what all these things mean. As a consequence, there's extra overhead for TCP when you use it to communicate between processes in the same device, where you don't need to have stuff like slow start. There's also unnecessary checksums because it's very unlikely that you're going to have your bits corrupted. And you don't need to handle network congestion. So there's lots of stuff you don't need if you're talking between apps or between apps and services on the same device. So to make this work better, they have this thing called the binder driver, which is in the kernel somewhere. There it is right there. And it's optimized for inter-process communication on the same device. There's various ways to program the binder driver. There's a messaging framework that you can use. And then there's also something called the Android Interface Definition Language, which is essentially a method-oriented facade atop a lower-level message passing mechanism. And you can use this in order to be able to make method calls in one app that show up as method calls in the other app. So you make a method call in one app as a client, and then that will be implemented by a method call in a server process. So you think that you're making method calls, but in fact, under the hood, there's messages being sent back and forth. And again, it's a bit beyond the scope of this class to talk about that in detail. It's very cool. I talk about this in some of the other MOOCs that I've done if you're curious. The binder driver is written in C and C++, and it runs in the kernel to enhance performance. So they did that so that they wouldn't have to worry about, they try to do things like optimization through shared memory and so on. And obviously, you as an application developer access through Java layers. And the Java layers handle all the low-level mechanisms of encoding and decoding the data so you can make what looks like method calls with binary data in one address space and then ship it over to a different address space and have it running properly in that address space. One of the other cool things you can do with the binder driver and the binder framework is you can actually have, say, the client implemented in Java and the server process could be implemented in C or C++, and they can talk back and forth quite nicely. Okay, so that's the end of the Android Linux kernel.